Hello, everybody. Today we talk about what's the difference between vector, algebra, and complex number theory. Complex number theory include algebra, complex number algebra, and also calculus for complex number. And the vector has a vector calculus. Before that, vector algebra. Okay, this is not a subject that you can find in any math textbook. Okay, today we're going to talk about something totally new, which you never hear from school or textbook. There's nobody talk about this. Okay, but if you flex your brain, you can you can learn math when you say, okay, school has a subject, complex number theory, I have to take that. Or school has a subject, vector calculus, or I have to take that. And they never talk about relationship between them. Okay, so you have to figure it out by yourself, because textbook doesn't tell you the relationship. Okay, here you will get very clear idea about what they are. Basically, I give you the conclusion first. Complex number theory can be incorporated into vector algebra and vector calculus, but nobody do that. The reason is, well, there's no really application like physics to use that after you incorporate it. Vector calculus is already good enough for the physics, and the complex number theory is mostly mathematics interest. Okay, so if you like this kind of video, please subscribe and click like, and here we start. Okay, the vector word, we take it two-dimensional, I and j, right? And any point is given by ax and ay for the vector a, right? Then b is going to be bxi, is a different notation, byj. Okay, so this is the vector. Complex number is I and real number, right? So complex number A is like ax plus ay I, and B is going to be bx plus by I, and here ax, ay, bx, by are all real number. Okay, so why we have a two kind to deal with the two-dimensional geometry and stuff? Have you ever thought of that? It's just mainly historical. It's nothing mathematical about it. So I show you how they can be immediately related. We defined vector multiplication this way. Right? And this is inner product of vector. We also define different type of multiplication. I, j, k, determinant, ax. Oh, this is three-dimensional, so we make it ij. How do you do three-dimensional from two-dimensional? From this, you eliminate this portion, right? So it's going to be, let's see, just directly write it. B y, let's see, by, there's no z, is 0. So let's do this. I, j, k, ax, ay, az, which is 0, and bx, by, bz, and I is going to be ay, bz minus, so I is going to be 0. Okay, so basically the vectors go A vector and B vector is go this way. This when you say this means arrow go from top of the paper to the other side of the paper, right? If vector goes this way, is vector is pointing from other side of the paper to you. Okay, so anyway, this is gonna be k vector. Okay, so two-dimensional, there's no outer product because k vector doesn't exist in two-dimensional world. Okay, so now we do this. Okay, we define new multiplication. From here, you have to flex your brain. Okay, and notation is not dot or x. We just temporarily use this. You have to be careful. This, as I said, the vector's direction, and also in the logic world, it's used as an exclusive or and stuff. So, but we temporarily use this. We define a b kind of multiplication, and how we define in this multiplication, I multiplied by I is going to be I multiplied by j is going to be j, and j multiplied by j is going to be minus I. Okay, so if you do that, then this is going to be ax, right, bx minus ay, by, that's I, plus ax, by plus ay, bx, j. So it's just like a x plus ay, I multiplied by bx, by equals ax, bx minus b, ay, by plus ax, by plus ay, bx, I. So this new multiplication we defined is going to produce exactly the same result as a complex number. Okay, that's it. So the addition, subtraction, multiplication, all defined, and they behave just like complex number. Only things what you have to do is define new multiplication in vectors, and definition is here. So it sounds like a complex number become just a part of vector, right? One more thing we have to know is it's possible complex number a x plus a y I can be divided. Okay. And what is the definition of division? Definition of division is basically multiplication of reciprocal number. And the reciprocal number, you calculate this 1 over bx plus by I is going to be bx square minus by squared bx minus by. So this portion is going to be the real part, and this portion will be imaginary portion. So if this is the definition, then we do the same thing. The vector, we define the reciprocal number of vector. That's interesting. Reciprocal number of vector. Why not? Even you learn the linear algebra's matrix has a reciprocal matrix. Reciprocal vector we define this way, right? It's going to be vector b's and bxi plus minus by j. So we define reciprocal of a vector, then we can do division just like complex number 2. Okay, so you got everything: add, subtract, multiply, and divide. So everything complex number algebra can do, the vector algebra can do. So it's a complex number. We don't need a complex number. We can do vector by defining this multiplication type. As I said, no textbook talk about this, okay? Here you have to flex your brain and think about so that you understand what you're learning. Complex number, wow, brand new. It's not really brand new. It's a different notation. It can be a part of vector algebra. Okay, how about calculus? How you define the derivative of complex number? Well, if you take a derivative respect to t, like a time, then it's going to be okay, so it's a multi-variable, multi-output type of calculus, right? This okay, so multi-variable, it can be depend on say you have a function I, and say this is x and y, that is x plus yi, and the function is defined using x plus yi has fx plus fyi. So multi-variable, multi-output. Okay, so the same thing we can do when we have a Navra, we talk about this one in vector calculus section. Okay, we have a different type of derivatives for vector A, and scalar f. It can be multivariable, right? Like this is a potential. You take a derivative and turn into vector. Right? And this one is going to be scalar because vector multiplication like that. So this is going to be like that, right? And this is going to be the vector. Again, this is a rotation or curl, they call, right? This is divergent. This guy is the divergent, and this is just gradient. Okay, so we define the new derivatives. This is going to be, the result will be exactly same as the complex number derivatives, and you can develop this. This is your own math here. This math do not exist anywhere, okay? And you can be the first person who developed the math using vectors, take over entire complex number theory, and the result is the same. Okay, so we don't spend too much time on this one, but you get the idea. The idea is complex number theory and vector algebra or vector calculus. Looks like you're learning totally different things. You're not. It's just a different notation, and by proper some additional definition, complex number theory can be absorbed into vector algebra and the vector calculus. Okay, I hope this story is interesting to you, and please do not forget to subscribe and click like. Okay, see you next video.